let's begin to introduce limits using an average velocity and instantaneous velocity. We'll go ahead and memorize the definition of average velocity and gain intuition of instantaneous velocity. We'll do this by analyzing numerically the slopes of the secant lines to estimate instantaneous rate of change, or estimate the slope of the tangent line at a certain x value. Remember, x is your independent variable. In many cases, in real-world situations, t could also be your independent variable. You may have all heard of the speed limit. If you're riding down a highway or freeway in a vehicle, you may have heard of 65 miles per hour. Speed is actually the magnitude of velocity. Once again, speed is the magnitude of velocity. Turns out velocity could be positive or negative, and we're going to see that through our next few examples. We're going to go ahead and analyze numerically these computations of average velocity, and then we'll use those computations to make a prediction at a very specific moment in time. And that very specific moment in time, we're going to go ahead and estimate something called the instantaneous velocity. So let's begin with an example. I do need to remind you of a slope formula, and that slope formula here is going to match the definition of average velocity. So if you look down here, there is the slope formula. It is the change in y values over the change in the independent values, or the change in dependent values over the change in independent values. You may have recalled this from algebra as m is equal to y sub 2 minus y sub 1 over x sub 2 minus x sub 1, where y is your dependent variable and x is your independent variable. In our first example, our independent variable is represented by time, so we use the letter t to indicate that. Nothing really special about computing slopes. You just gotta make sure you understand which one is t sub 1 and which one is t sub naught. So let me write it over here. In your interval here, this is t sub naught, and then up to t sub 1. So from t naught to t1, that will become your time interval. The slope formula says to evaluate the first one here. Let's go ahead and evaluate the first one. The first time interval here, we're going to evaluate s of 2.5 minus what? Minus s sub 2 all over 2.5 minus 2. And then you go ahead and pound this out using a calculator and order of operations. Be careful with order of operations. Make sure you're doing that correctly. So you might want to make use of a bracket. And go ahead and take a moment and pound this out using a calculator. Notice the time interval here is only half a second. And if you evaluate this using a calculator, you'll eventually get exactly negative 32 feet per second. Now, I'm not going to bore you with a whole bunch of computations regarding slope. But what you want to pay attention to is the numbers. Is actually the numbers in the column of the table. So repeating this process with different time intervals, the time interval is getting shorter and shorter. That means the t values are approaching t equals 2 from the right-hand side. And what you want to do is pay close attention to the numbers. Is it still positive? Is it negative? And what number is it approaching? As the t values approach t equals 2 from the right-hand side. Now you're probably wondering, what do I mean by t values on the right-hand side? Well, there's a t-axis, and there's a moment called t equals 2 seconds. Notice 2.5 was starting on the right-hand side of it, And then we went to what, 2.1, and then we get even closer and closer, 2.01 eventually. Okay, so as t values approach t equals 2 from the right hand side, what happens to the average velocity? And you can see that the numbers here represent the average velocity, and you want to make a prediction. Where is this average velocity going? Make a prediction of make a prediction of what the velocity will be when t equals 2 seconds. Go ahead and write your prediction down here. This prediction is actually going to be called the instantaneous velocity. So when t equals 2 seconds, or at the moment of 2 seconds, the instantaneous velocity is going to be, now I really don't know. I'm just going to take an educated guess just by the numerical values there. I'm going to guess negative 24 feet per second. Okay, so at the moment of t equals 2 seconds, I'm going to guess the instantaneous velocity. We're going to do a similar thing with a second example. Now, you may have learned how to draw a quick sketch of this from your trigonometry class. A sinusoidal curve. You're expected to know how to draw these rather quickly. This is a home function with an amplitude of 3. I call these the home function, meaning it's your sine wave, but your only thing that changes is your amplitude. And of course, these are periodic, so these go on and on and on forever. But that's usually your typical first period of a sine wave, 2 pi, pi, and so on, and pi over 2. And the thing you want to take note is your amplitude, or your displacement here. Your amplitude is 3. So it goes 3 up, and then it goes 3 down, and you can really see the amplitude. Now this time, it's a position of a block that's on a spring. So imagine a spring here that has a block tied at the end, and it's just bouncing up and down. So it's going back and forth, bouncing up and down, and that is actually measured by this function. I should say the position of this block is measured by the function right here, by this sinusoidal wave. Now we're going to do a similar thing. You're going to be given a time interval, and you're just going to compute the average velocity for this block. So just a reminder here, just like the first example, you're going to have an interval here, t sub 1, t sub naught up to t sub 1, and we'll go ahead and evaluate that using your experience of trigonometry. So the first one is going to be the average rate of change, or the average velocity. It's evaluated at s sub pi minus s of pi over 2, all over what? Pi minus pi over 2. This expression will have the same value as 3 times the sine of pi, that's just 0, minus 3 all over pi over 2. And notice we get negative 6 divided by pi. Once again, I'm not going to bore you with all these calculations, but I will go ahead and give you some approximations here, some decimal approximations of these values. Once again, notice the pattern, okay? Notice the pattern of numbers. You're going to use this pattern of average velocities to make a prediction of when t is exactly pi over 2, or at the moment of t equals pi over 2, what would be a good prediction here? This time the units are in inches per second. So it seems like the average velocity is getting smaller and smaller and smaller. So as t values approach pi over 2 from the right, my prediction of the instantaneous velocity at t equals pi over 2 seconds is 0 inches per second. One more example, very similar, but this time we're just looking at algebra. We're looking at a rational function from algebra, and we're going to go ahead and approach this point P from both sides. I should say the x value equals 1 from both sides. So we're going to first approach x from the left-hand side. So I could write this down. We're going to first approach x from the left-hand side. So x approaches 1 from the left-hand side. And we're also going to approach x approaches positive 1 from the right-hand side. And this time we are just going to compute the slope formula just like you did in algebra class. Just realize that this first point P is going to be x1 comma y1, and that is fixed. And then point Q is going to be x sub 2 minus y sub 2. So notice your point Q is different every single time. And we're going to compute the average rate of change, or in this case, the slope, right? The slope between 2 points. Okay, you're just computing the slope between 2 points there, slope between this one and this point. And you're just going to do that just like you do from algebra class. You're going to need a calculator. So go ahead and, crunch these numbers just like you did in the previous 2 examples. And then make sure you are getting these decimal approximations. If you want to, you could pause the video just to make sure you are computing these slopes correctly. Do a few of these slopes first, and then you could unpause the video to check your computation. The double tilde symbol means approximately. So it's not a double bar symbol, but it's a double tilde symbol. Double bar actually means to have the same value as. So if you're wondering what double bar means, it means is to have the same value as. So take a good look at these numbers and see if you can make a prediction of what the actual slope of the tangent line will be. What is the actual slope when x equals 1? And one of the classic, very, very popular calculus question is, can we find the equation of this tangent line? Assuming that you know the instantaneous rate of change, or assuming that you know the slope of this tangent line, can you find the equation? Of course you can. If m is equal to 1/4, and the point of interest is actually 1 comma 1/2, we could simply use the point slope formula to get the equation of this tangent line. Now you got to remember, slope y-intercept form represents y equals mx plus b. However, point slope form is this formula. And we'll go ahead and evaluate this or simplify this equation by making appropriate substitutions. So this is simply algebra. And notice you do get the equation of the tangent line to that function when x equals 1. Gotta write the slope back in. And there you go. There's an introduction to average velocity and instantaneous velocity. Just think of the word instantaneous meaning at the very moment, at a very specific moment, instantaneously, at the snap of your fingers.